Hi everybody, I'm Isha.
And I'm Jenna. Today we're going to be talking about an AP Physics build project that we did. It was a trebuchet. Our objective was to have it go at least 45 to 50 yards and take down a castle.
So before we get into anything, we had to do research, so we're going to show you what we found. Before we could get started building a trebuchet, we had to understand the physics behind it. On one side of the beam, there is a heavy counterweight with high potential energy, which is energy at rest due to its height. When the counterweight is dropped, the potential energy transfers to the beam in the form of kinetic energy, which is energy from movement. The energy then continues to move into the sling, and then this energy launches the projectile, and along with the angle release, determines how far the projectile will go.
While researching, we found four main types of trebuchets. The first was a floating arm trebuchet. At first, we leaned heavily to creating this type because it was of the most energy efficient. It has a counterweight that falls in a direct path, which allows for greater conversion of energy to the projectile. Potential energy is maximized by having a super propped counterweight and a horizontal guide track. Both features also allow for a greater drop height. All three features allow for the projectile to travel great distances. However, we decided not to build this type because it would have been very difficult to get it built and tested in time. The King Arthur trebuchet was another type that we were leaning heavily towards. With its two-trigger system, one for the counterweight, the other for the long arm, it is very accurate. It has a very unique cock position, which is the position before firing, as well as a super propped counterweight, which allow for maximum potential energy. This type of trebuchet also has one of the smallest projectile weight to counterweight ratios, meaning that it can go very far distances using very little counterweight. The King Arthur is also very tunable, meaning that it is easily adjustable to go the desired distance. Ultimately, we rejected this trebuchet for the same reasons as a floating arm trebuchet. It would be very difficult to build within our limited time frame. The fixed counterweight trebuchet also did not make the cut. It was simple enough to build, but not very accurate, and one of the least efficient type of trebuchets. Therefore, we rejected it. We ultimately decided on the hinged counterweight trebuchet because it's relatively energy efficient and easy to build. Some risk associated with the trebuchet surrounded the axle and the counterweight. Since the counterweight was not super propped, there was increased shock on the axle, meaning it could break more easily. We thought that getting a thicker and stronger axle could avoid this problem. There was also the risk of not having enough potential energy because the counterweight was not super propped, but we realized that adding more weight could achieve the same effect. We also used a very short rope to minimize the twisting of the counterweight and maximize the height, thereby maximizing the potential energy. Once we decided what trebuchet to use, we had to figure out the ratio to use while building. We used research by Donald B. Ciano in order to find these. We then proceeded to use things like trebuchet simulators to test the ratios that we found to work. We ended up with mixed results. The simulator that we used did not give us information that we believed to be accurate. For example, if we entered in the same ratios twice, it would give us completely different results. In Home Depot, we got down to business, and one of the most difficult decisions we faced was deciding what type of wood to buy. We ended up looking at a huge selection of wood and having to really think about what we wanted. We started out looking for 2 inches by 4 inches by 16 feet, planks of wood, but that ended up not being able to cut down the way we wanted. So we went back on the hunt and found 2 inches by 2.5 inches by 8 feet planks of wood, which cut down perfectly. We also found a rectangular board that was 4 feet by 4 feet that we used as a base once we cut it down to 2.75 feet by 2.75 feet. While also shopping for some wood, we ran into some friends. We also picked up a 1/2 inch diameter wooden dowel, L joints and nails, and some duct tape. Afterwards, we got some elastic and twine from Michael's.
Using a protractor and a 2.5 feet long wood piece, we measured 45 degrees from one side and 15 degrees from the other, making it so that opposite edges are pointed. We then sawed the angles off using long but slow strokes. We repeated this twice on 2 different 2.5 long pieces. Then we took the extra 15-degree wedge we cut off and wood glued it and nailed it to the bottom of an unsawed 2.5 feet long wood piece. This step was repeated twice. Next, we took the wood piece with the 45-degree cut on it from step 1 and glued it to the straight edge wood piece from step 2. We then screwed L joints on both sides, and we repeated this twice to make 2 triangular shapes. We then drilled a 0.5 inch hole about 2 feet from the base of the triangular pieces, about 1.5 inches deep. We repeated this process for both triangular pieces. Next, we marked 3 inches in from each corner of the baseboard, and then we glued the triangular pieces across from each other with the drill holes facing in on the marked points and reinforced with duct tape. Flipping the baseboard over after the glue had dried, we proceeded to nail in each edge of the triangular pieces in as extra support. We then measured the distance between each hole in the triangular pieces and cut the dowel to that length. Next, we took out a 4 feet 2 inch piece of wood and marked on one end where we would drill a hole all the way through using a 3/8 drill bit for the counterweight. We measured 1.5 inches in from the length and 1 1/4 inches from the side, and we found our point where we drilled a hole. Measuring 1 foot in from the drilled end and 1 1/4 inch from the side, we drilled another hole with the 1/2 drill bit to act as the pivot separating the long arm from the short arm. We then pushed the dowel through the 1/2 inch hole and wood glued it to both holes of the triangular pieces. Then we duct taped on both sides of the pivot around the dowel and the arm to ensure the arm would not move side to side. On the other end of the long arm, we hammered a nail halfway into the edge to attach the sling. Then we cut a tennis ball in half, poking holes into each side of the halved tennis ball. We then strung a 4 foot 5 inch string into the holes of the halved tennis ball. Afterwards, we covered the tennis ball in a light cloth with a narrow slit in the middle to ensure the bouncy ball can be released from this sling. Then both ends of the string were tied around the nail. Taking 2 5-pound plates, we strung a rope through them and secured it to the 3/8 inch hole in the short arm, tying it up as high as possible.
One of the biggest problems we had with our trebuchet was the sling, because it kept shooting backwards or having the ball roll out and not shooting at all. In order to combat this, we went through 3 different sling materials and a different bow before settling on the one we used. We ended up using a string for the sling and a half tennis ball covered in cloth in order to keep the bowl from rolling out. When getting our trebuchet to school, we had some difficulty because it wouldn't fit in a regular sedan. We had to borrow a minivan in order to actually have it fit in the car.
Soon test day came along and we performed 5 trials with our trebuchet. In each trial, we found the distance the projectile traveled using a meter stick, and we found the time the projectile was in the air using a stopwatch. We found that our percent efficiency was 0.2%, which was not ideal. The biggest problem we had in our trebuchet was our dowel. Our dowel could not sustain the pressure it received from the arm, so on test day, it snapped. So next time, we're thinking of using a metal rod or a steel rod in place of the wooden dowel, so it could actually sustain the energy or sustain the pressure and not lose any energy.
Since we lost a lot of energy in the dowel, we ended up not having enough torque to have the trebuchet launch properly. So I ended up launching backwards, and and it didn't go the distance that we wanted it to.
We hope that this video helps you design and build a trebuchet that goes 45 to 50 yards.
Thanks for watching. Bye.